So today's lesson is on different types of number sets. So let's start by completing the blanks. Real numbers are all numbers. We use the letter R to abbreviate. All numbers, meaning any number that exists. Rational numbers, we use Q to abbreviate, and those are numbers that can be written as a ratio or a fraction. So any number that you can turn into a fraction easily is rational. So for example, if we have a whole number like 7, 7 is rational because it can be represented as 7/1 or 28/4. Both of those are equivalent to 7 and are fractions. Therefore, 7 is rational. A fraction or a decimal like 0.5 is rational because we can write it as 1/2. A fraction like 0.975 is rational because we can write it as 975/1000. And any number that repeats is also rational because those can be turned into fractions as well. So any number that repeats actually can be put over a denominator of 9 or 99 or 999. So for example, if you have 0.2 repeating, that's equivalent to 2/9. And I can prove it to you by doing 2 divided by 9. And I get 0.2 repeating. Something like 0.24 repeating would be 24/99. And again, I can prove it to you if I use my calculator. I do 24 divided by 99, and I get 0.24242424 and so on. Okay. And lastly, if I have something with 3 digits repeating, something like 0.367 all repeating, that can be written as 367/999. And again, if I prove it to you, 367 divided by 999 is 0.367367367 and so on. So that proves that any repeating decimal can also be written as a ratio or a fraction and is therefore rational. So think rational and repeating, think rational and written as a fraction. Anything that cannot be written as a rational number or a fraction is what we call irrational, the opposite of rational. Irrational numbers are numbers that cannot be written as ratios. They're non-repeating, non-terminating decimals. So a really common irrational number is pi. Okay, pi is a non-repeating, non-terminating decimal number. It keeps on going and going and going without a pattern, therefore it's irrational. Other common irrational numbers are the square roots of numbers that are not perfect squares. So for example, the square root of 20 is, if I use my calculator, 20 and then square root, I get 4.472135595, and it keeps on going. And in that whole long string of numbers, we do not see a pattern. Therefore, it's irrational. Or square root of 5. So if I do 5 in square root, I get, again, a long string of numbers without a pattern, so it's irrational. Unlike numbers like square root of 25 or square root of 4, because square root of 25 would be exactly 5 because 5 times 5 is 25, and square root of 4 is exactly 2 because 2 times 2 is 4. So those are rational numbers. Okay. Within the rational numbers, there are 3 other number sets, and those are natural numbers we use N for, and those are what we call the counting numbers. So you start counting with the number 1. Therefore, counting numbers are 1, 2, 3, 4, 5, 6, and so on. Nothing in between. Whole numbers we use W for, and that's the set of natural numbers in 0. So I like to say it's the number set that starts with a whole, and 0 is a number with a whole in it. So 0, 1, 2, 3, and so on. Not anything in between, so no fractional parts. And lastly, we have integers, which we use Z for, and that's a set of whole numbers and their opposites. So all the negative and positive whole numbers. And keep in mind that it's negative and positive whole numbers. So just because a number has a negative attached to it does not mean that it is an integer. So something like negative 2.5 is really not considered an integer because it has the 0.5 added to it. It's only rational, not an integer. All right, so keeping that all in mind, and the idea of rational and irrational with square roots, and it's important to be able to identify if something is rational or irrational based on its square root. So when the square root of a number results in a whole number, it is rational. If the square root of a number is not a whole number, it is irrational. So I'm going to do a couple examples with you so you see where I'm getting my answers from, and then you're going to try a few on your own. All right, so for the first one, we have negative square root of 25. So 25 is what we call a perfect square because you can take the square root of 25 and get a whole number. Think about what number times itself makes 25. Hopefully, you're thinking 5 because 5 times 5 is 25. So the square root of 25 is 5. But because of the negative sign on the outside, it's negative 5. Since we're able to take its square root and get a whole number, this is what we call rational. And now in the directions, it does say to circle the rational one, so we're going to circle number 1. Number 2, square root of 121. Again, if you're good with your numbers, if you think about, well, what is the square root of 121? Is there a number times itself that makes 121? You can do it in your head. If you can't, you go to your calculator, put in 121, take the square root, and we get 11 because 11 times 11 is 121. So again, we get a rational answer. And we circle it. Number 3, again, you want to think about, well, do I know a number times itself that makes 90? Can I do the square root in my head? If you can't, go to your calculator, square root 90, and that is a long string without any repetitions. So it does say in the directions to round to the nearest tenth. So we're going to write approximately 9.5. And since we had to estimate and there was no pattern there, we can't write it as a fraction. This is irrational. Okay, I'm going to do 2 more with you, and then you're going to be on your own for 6, 7, 8, and 9. So for number 4, we have the negative square root of 12. Think about square root of 12. Is there a number times itself that makes 12? I personally can't think of one. It's a small number, so I should be able to get it off the top of my head. So we're going to do 12 square root. And again, we get 3.464101611513, and so on. There's no repetitive pattern there, so we cannot turn it into a fraction. Therefore, this is irrational. And again, we want to estimate it. This would be negative 3.5. All right, and then lastly, we have the square root of 400. If you can think of a number times itself that makes 400, then it is what we call a perfect square. If you can't, you're going to quickly just do 400 and square root, which gives us 20, which is a whole number. So 400 is what we call a perfect square. Its square root is 20. So now 20 is a rational number because we can write it as a fraction. Okay, so far, 3 of those problems are rational. You're going to try 6, 7, 8, and 9 on your own. You can pause the video here and do it now, or you can come back to it later. Okay, on the back, we're going to organize the number sets into a graphic organizer, which we can use to then place numbers in the right sets. So again, the all-encompassing number set is what we call real numbers. Then within the real numbers, we have 2 main sets. We have rational numbers, and we have irrational numbers. Irrational numbers are all by themselves because if a number is irrational, it doesn't fall into any other category other than real numbers. Within the rational numbers, we have 3 other sets from greatest to least. The next biggest set under rational numbers would be integers because those are your positive and negative numbers, whole numbers. Within the integers, we have whole numbers, And within the whole numbers, we have natural numbers. Natural numbers are the smallest set because they only contain the numbers you count with. So 1, 2, 3, 4, and so on. Whole numbers is one number greater than natural numbers because it has 0 and 1, 2, 3, and so on. Then integers is double whole numbers because it's the negative and positive whole numbers. And then rational is, again, all those decimals or fractions that you can write, or decimals that you can write as a fraction. And real numbers is everything. So now we're going to take our numbers and start putting them into number sets based on our graphic organizer. So for -6, we have to think about, well, what is the smallest group that -6 fits into? So again, I'm just going to write it here so I can show you. It's real, and then rational, irrational, integers, whole, or natural. So for -6, -6 has a negative attached to it, and 6 is a whole number. So the first category it's going to fit into is integers because of it being a negative whole number. And then we work our way up our graphic organizer. If it's an integer, it's also rational. If it's rational, it's also real. So we write integer, rational, real as our response. Then we have 8 and 2/5. So 8 and 2/5 is a fraction. 2/5 cannot be changed to a whole number. This would be 8.4. So it's not natural, whole, or integer. The first category it would fit into is rational. So it's rational and real. All right, next we have pi. Pi, again, is 3.14159, and it keeps on going and going and going without a pattern. Because there's no pattern in that decimal, it is irrational because we cannot write it as a fraction. If a number is irrational, it is still real. Okay, next we have the square root of 2. If you take your calculator and do the square root of 2, you get a non-repeating, non-terminating decimal. So it cannot be written as a fraction. So it is irrational and, once again, real. Okay, next we have 5.3 repeating, which hopefully you remember from earlier in the lesson. We talked about how repeating numbers can be turned into fractions. And hopefully you remember that I said if it's one digit repeating, it can go over 9. So this is 5 3/9, which some of you know as 5 1/3, because 3/9 can be simplified to a third. That is a ratio, therefore it is rational. And if a number is rational, once again, it is also real. Okay, next one, number 6, we have 0.05. Well, 0.05, we have the 5 in the hundredths place, so this is 5 hundredths. We could simplify that further, it would be 1/20th. Since I can write it as a ratio or a fraction, it is rational and real. Okay, so you are on your own for 7, 8, 9, 10, 11, and 12. I'll be around to help you out.